Equilibrium in statics refers to Newton's first law, where the sum of forces acting on a body is zero, resulting in zero acceleration. To better understand this concept, let's look at an elevator in equilibrium. Most of us ride elevators every day when we come to school, go home, or go to work. This elevator is at the CEDETEC building at the Tecnológico de Monterrey, Ciudad de México campus. Let's analyze the different components in this elevator system. As you can see, the elevator is being pulled up by 6 cables that go around a series of pulleys. The elevator has 2 pulleys at the bottom, each with 6 grooves to support the 6 cables. One side of the cables goes up, where the cables are attached to springs supported by the ceiling. The other side of the 6 cables go up and around a rotor. From the rotor, the cables go down and around another pulley that supports a set of weights with the purpose of countering the weight of the elevator box, lessening the torque required by the motor to pull the elevator up. Finally, the 6 cables come up from the counterweights and again reach springs supported by the ceiling. When the elevator is not in motion, all components in the elevator are in static equilibrium. When we do our analysis, we need to draw free body diagrams for each individual component. Let's look at the counterweights first. The weights are supported by the pulley, which in turn is supported by 6 cables going around it. Assuming the pulleys to be frictionless and of negligible mass, the forces involved in this system are the weights of the counterweights pointing down and the tension on the cables pointing up. Since it is the same set of 6 cables on each side of the pulley, and our system is in equilibrium, the value of the tension is the same in both sides. From the equilibrium condition that the sum of forces is equal to 0, we get that the weight of the counterweights equals twice the tension of the counterweight cables. Now let's look at the elevator box. The forces associated with this system are the weight of the elevator, the tension of the cables, and the weight of the people inside the elevator. Following the same logic as before, in this case, twice the tension will equal the weight of the elevator plus the weight of the people inside. Now let's look at the rotor. Assuming negligible mass for the rotor, the forces acting on the system are the tension from the elevator, the tension from the counterweights, and the reaction force at the rotor axis. Again, solving the equilibrium condition yields that the reaction force of the rotor has to equal the tension of the elevator plus the tension of the counterweights. Here's an interesting question. Is the tension from the elevator cables the same as from the counterweights? The answer is not necessarily. If they are equal, this means the combined weight of the elevator and the people inside it is the same as that of the counterweights. Then there needs not be any torque from the rotor to keep the system static. However, if they are not equal, this difference creates a moment about the axis of the rotor, which must be countered by an opposing torque. For example, if the tension of the counterweights is less than the tension of the elevator, then the resultant moment is clockwise. In order for the system to remain in equilibrium, the rotor needs to apply a moment counterclockwise with the same magnitude. Remember, to define equilibrium in this system, we need for both the sum of forces and sum of the moments to equal 0.